Hi everyone, this is a classic physics problem with air pressure. There's a limit to how high air pressure alone can raise a column of water, and we want to know what is this maximum height on planet Earth if we happen to be at sea level. So let's take a look at what the actual situation is. Let's say you have got an open tub of water and you have a tube, a long thin tube stuck into it, and it's supported accordingly so that it doesn't fall over. So down here we've got water. Now how are you actually going to make the water rise up the tube? Well, you're going to put some sort of a vacuum up here. And that vacuum can be produced by a pump. It could be produced, if you want to treat it like a long straw and have somebody try and, suck on this end, whatever works for you. This is going to create a vacuum here. And the best vacuum you can create is no air. So how exactly does the water rise up the tube? Well, you're counting on atmospheric pressure pushing down, and actually, as this is a vacuum, the atmospheric pressure is going to make the water climb up the tube. And because of the weight of air on planet Earth, there are numbers that determine how high this column right here is actually going to get. Now, how are we going to calculate that? We're going to use the equation for determining pressure at depth in a fluid. Pressure is density, height, acceleration of gravity. And what we're interested in is height. So height is going to be pressure divided by the density of the fluid and the acceleration of gravity. So in this case, the pressure, we are going to be at sea level. So the pressure of what is pushing down here at sea level, that is going to be a 1.013 times 10 to the 5th pascals. That is the sea level pressure, divided by the density of fresh water, 1 times 10 to the 3rd kilogram per cubic meter, and the acceleration of gravity, 9.8 meters per second squared. So when we do that, the height ends up being 10.34 meters. That is the maximum height. By creating a vacuum, you can use plain old atmospheric pressure to push a column of water upward. Now let's take a moment and look at the units, because the units here are kind of messy. So we have a pascal. A pascal is a Newton per square meter. That's what a pascal is, divided by a kilogram. The meters cubed is in the sub-basement, so that's going to come up here, divided by meters. Seconds squared are in the sub-basement, so that's going to come up here. And this is still kind of messy, so I'm going to take newtons and expand it into its constituent parts. So a newton is going to be a kilogram, meter per second squared, all of that is a newton, divided by meters squared, kilogram meters, I'm just recopying this, meters cubed, and seconds squared. Now we can do some heavy-duty canceling. Let's see what we've got. Kilograms on the top, kilograms on the bottom. Seconds squared on the bottom, seconds squared on top. I've got meters, 4 meters on the top, and 1, 2, 3 meters on the bottom. So the meters on the bottom will cancel the meters cubed. I am left with meters. Meters is a good measurement for height, and that's where those crazy units come from. Now, there is no second part of this problem, but I'm going to throw something out just for giggles, and that is the concept that what if we were using a more dense fluid? Very often in barometers, they did not use water. They actually used the liquid metal mercury. Very dense liquid metal. But by using a very dense liquid metal, what that did is they made the height much, 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 much shorter. 10 meters high, 10.34 meters high, is right around 33.9 feet high. And by using something that was much denser, the common mercury barometer could then be about the height of somewhere around 3 feet high. So it made it manageable and something you could actually have in a laboratory. 10-meter high, barometer, kind of tricky, and it would freeze in the wintertime, so never a good idea. All right, we'll see you next time.